All right, so today's lecture number 8, and let's quickly go through what we've discussed last time. So we've started discussing the quantum gates and quantum circuits, right? We quickly recall this quantum classical gates in classical computing. Gave a couple of examples. Example of NOT gate and XOR gate. NOT gate is an example of a reversible classical gate. XOR is not reversible classical gate, and the logic of this XOR, for example, this XOR gate is given by this XOR sign circle plus, and yeah, and then we say that in contrast to classical computing, in quantum computing, all gates must be unitary and must be represented by unitary operators, because we want to keep the inner product of the vectors unchanged. For example, it leaves unchanged the norm of a vector, which is given by the inner product of the vector by itself. Why it's important? It's important because these operations don't mix up the things, don't spoil our normalization, so we can use the vectors and the amplitudes of the vectors as the probability amplitudes. All right. So having this said, we started discussing the single qubit gates. The first one is X gate, or bit or qubit flip gate. Essentially, it rotates the vector state in the block sphere representation around the axis X. So, for example, the Z state, it sorry, this state 0, it flips to the state 1, or the state plus I, it makes it transforms to the state plus I or minus I. Z gate does similar things, but rotates the state around the axis Z. Y gates acts in the similar way. It transforms the vector by rotating it around axis Y. And then we introduce this important Hadamard gate. So this Hadamard gate creates, the purpose of this gate is to create the superposition of states. For example, if we start from the state 0, this Hadamard gate creates state plus, which is perfect superposition of state plus and minus, of state 0 and 1. Okay. And some other gates which we can call phase gates. The most general one is P gate, which rotates, changes the phase by this angle alpha. Alpha is a parameter, and this alpha can acquire any number. And for example, if alpha is equal to pi over 2, then this gate is known as S gate. If the alpha gets value pi over 4, then it's known as T gate. And in general, any single qubit gate can be represented by this matrix here. Okay. So of course, these all these gates are rather theoretical, right? It's a perfect. In reality, nothing is perfect, and in real systems, there is some inaccuracy of the applying of the gates, and for example, using this U gate, one can describe the action of the actual gate in a real life system. Okay, but in order to compute the things, one qubit gate is not enough. We need also 2 qubit gates, and we've started with discussion of the most important one, which is known as C0 or CX gate. So CX gate acts the basically it acts as a X gate depending on the state of the control qubit. So this 2 qubit system, 2 qubit gate, C0 gate, it gets control qubit and target qubit. And if control qubit gets state 0, then this gate does nothing, no action on the target. But if control gets state 1, then this C0 or CX gate acts as a X gate to the target qubit. Okay, so if control is 1, then and target, then it converts target from 0 to 1 and from 1 to 0. And important point here to understand is that, like in reality, in computation, the state is almost never either 0 or 1. Okay, so it's some combination, some superposition of 0 and 1. And the way this gate acts, it applies, so it basically converts the both options, right? It takes both options. So if this gate gets the superposition of zeros and ones, and the input and the output will be also the superposition of all these 4 possibilities at the same time, simultaneously. Okay, so this is another manifestation of quantum parallelism. Okay, so this quantum gate applies or works for all the possibilities at the same time. Okay, and then we discussed all these examples and particular gates, illustrating them using this IBM quantum platform, the system that we're gonna use today quite extensively. And the last one, probably, yeah, the last topic was about this golden 2 qubit circuit. So this is one of the most important circuits in quantum computing. Why? Because it allows us to create the entangled Bell states. Okay, so we describe this circuit, which consists of 2 gates. One is Hadamard gate applied to the first qubit, and then the CX or C0 gate applied as a control to the first one and target to the second one. Okay, and after these computations, we find out that the output state from this circuit is the superposition of state 0,0 and state 1,1, which is perfectly entangled, non-separable state a truly quantum state with no examples in classical physics. Okay. At the same time, since Hadamard gate and CNOT gate, they both are unitary, right? And the combination of two unitary operators is another unitary operator. So this golden two-qubit circuit can be described as a unitary operator, which gets the state 0 and 0 in the input and converts it to the Bell state in the output. Okay, and the same reason, the same fact that this circuit is unitary allows us to inverse this circuit, okay, and use the circuit in the way, the reversed way. Use the circuit as the circuit that converts the Bell state back to the basis states 0 0. Okay. Yeah, and we mentioned that there are 4 types or 4 kinds of Bell states. We discussed one here, and other Bell states can be also generated by slightly different circuits. For example, this Bell state of the second type requires just another single qubit gate. There, this X gate to be applied to the first qubit. I'm talking about this circuit here. All right. So using quantum gates, we can basically design a quantum circuit that does something interesting to us, something useful. And a lot of people, a lot of researchers, quantum engineers, they and quantum information theorists, they strive to develop the quantum algorithms that use quantum concepts, quantum effects like superposition and entanglement to do something useful for us. Okay. Yes, and maybe yeah, maybe one point to notice here is the difference between just any quantum computer and the universal quantum computer. And the difference here is just the same as in classical computation theory. Like any classical physical system can be considered as a computer, right? Like, for example, a pendulum can be considered as a classical computer, classical analog computer that gives us some answers, but very specific, very particular answers. Like, what if, what would happen if I change this pendulum somehow? What would be the reaction? What would be the trajectory of this pendulum? Whatever, any classical system can be thought in terms of computing. Okay, analog computer. So like, instead of calculating the trajectory of the pendulum or any other system, you can build the structure, build the pendulum, and then do the experiment. And this experiment will give you the answer. Okay. But this is something that I mean, that's nice, but we need something more universal, right? Like a digital universal computer, like a desktop we have, where we can run any type of computation, simulation, etc. In quantum computing, the situation is similar. Like any let's say atom can be considered as a quantum computer, which gives very specific answer, like the states of the specific atom. Okay, or like Fourier transform. You know, this operation of Fourier transform. Fourier transform can be done in experiment using just one lens. You take one lens, and the lens can do the special Fourier transform. So you don't need any computation to Fourier transform the things. You can just apply the the single lens. But this is not universal. We need something more general, or something that can be used for any system. And that's why the quantum computers, as well as classical computers, they are designed in a way to be universal. So you can run different types of quantum computations. And of course, the quantum computers can be of different different topology. And today we will meet with a couple of them. So right now, I suggest that we start with a couple of maybe examples. So first of all, it was lecture number, well, it was 7 or 8, 7. So today is number 8. Lecture number 8. Okay. And let's call this one maybe just Qiskit. Okay, so the Qiskit. So Qiskit is the IBM platform based on Python that we're gonna use to simulate quantum circuits. Okay, but before going to IBM quantum computing, let us maybe describe a few other things. So first of all, in Qiskit, in IBM quantum platform, you can also find or meet another type of 2-qubit gate known as swap gate. And the purpose of this one is straightforward, right? So it just swaps the qubits, the states of the qubits. So it's denoted by this circuit element, just two crossed connected, and yeah, and the operation is very simple. So if in the input you get states AB, then after the swap gate you get the state BA. Okay, like if you have state 0, 1 in the output, you get state 1, 0. And again, since this is the quantum gate, it conducts all possible operations simultaneously, okay? Because the input state is also can be a superposition of all possible states in the that two qubits can take. This is one node. Another node is the need for the measurement. So the quantum circuit does the computation, but we need to add so well, let's maybe write this one like a node 1, node 2. So node 2 measurement. Measurement. So any quantum circuit eventually gets the measurement gate. So measurement gate in IBM Quantum, let me, yeah, it's denoted by this rectangle with this scale, like this. And also gets this later Z there, which denotes the main basis, the main Z basis. Measurement in Z basis. Zero basis means 0, 1, right? The state 0 or 1. And so usually, typically, this is the very last gate in the circuit, and it gets the quantum qubit in the input and returns the classical state in the output. So this is classical, this is quantum. So we put this measurement gate. So, and of course, this measurement gate is the only irreversible gate of the quantum circuit, because it does the non-reversible things. The quantum, the measurement, right? The measurement is something spontaneous, not spontaneous, but random. If you have, if the qubit can acquire two different states, then after the measurement, the qubit gets one specific state, but among the two, but randomly. Okay, and of course this operation is not non-reversible. Okay, this is the another node that we will need today, and probably let's consider an example of a circuit. So let's make example 1. And as an example 1, I suggest that we consider the, let me see, yeah, I suggest that we consider these GHZ states. GHZ states. This GHZ stands for Greenberger, Morne, Zeilinger. So the three scientists that proposed this state. So Greenberger, Morne, Zeilinger. Grr. So essentially, this is the generalization of the Bell states. Generalization. Generalization of the Bell states. Right. So, so the Bell state is something like 1 over square root of 2, then this 0, 0 plus 1, 1, superposition of the states 0, 0 and 1, 1. Okay, so entangled state, and this state gets the total entanglement, right? It's not separable state. But of course, this is the state of 2 qubits, but one can ask, like, can I come up with the more general state like this, for example, the state 0, 0, 0 plus state 1, 1, 1. Is it possible? Of course, it's possible. We just need to add another third qubit and entangle the third one with the rest of the circuit somehow. And this type of states is exactly known as GHZ state. So in this case, this is the GHZ free state because of free qubits. In general case, one can design GHZ N state. Okay, so we just need to add or use n qubits. So we denote it by like this. So zero state taken tensor product itself by n times plus state 1 again to the power of tensor n. Okay, and as an example, we consider the GHZ state with 3 qubits, and how we can, or let's show that we can generate this GHZ3 state using this 3 qubit circuit with 1 Hadamard and 2 CX gates. Okay. So as usually, we assume that the inputs are in the ground 0, 0 state. Okay. And we consider the circuit by layers, layer 1, layer 2, layer 3, and layer 4. 1, 2, 3, 4. Okay. So what happens in the first layer? First layer is just the tensor product of all 3 qubits. They all are in the 0 state, so the only state in the first layer I have this one triple 0 state. So what happens in the second layer? The second layer is after the Hadamard gate applied to the first qubit. I remind you that we count the qubits from right to left. So this is the first, this is the second, this is the third. And actually in quantum computing as well as in classical, we count the qubits from 0 to, so the first one is 0 qubit. The second one is first, and then second, etc. And I apply this Hadamard gate to the first qubit. And you remember the purpose of the Hadamard gate, right? So it gets the state 0 and it creates perfect superposition of state 0 and 1. This is the purpose of the Hadamard gate. So I apply this Hadamard gate to the first qubit, and I split this 000 state to the state 00 of the second and third, and then tensor product, Hadamard gate, and the state of the first one. Okay, so what I get in return, state 00, then 1 over square root of 2, tensor, state 0, state 1, state 0, state 1. And I now take the tensor product, so I get 1 over square root of 2, then state 0, 0, 0, plus state 0, 0, 1, 0, 0, 1. Okay, so this is the second layer. What happened in the third layer? The third layer is the state after applying the CX gate. Okay, so CX gate, this, or C naught gate, what it does, it acts on the 2-qubit system, right? In our case, it is qubit 0 and qubit 1. And depending on the state of the control qubit, which is this first one, the control qubit, it changes or doesn't change the state of the second or target qubit. Okay, so in this case, for example, the control gets state 1, so we're supposed to change the state of the target, flip the state of the target to state 1. So in return, we get 1, 1. So this is just an example. And I applied now this CX gate to our state 0, 0, 0 plus state 0, 0, 1. Okay. So the control, let's denote the control here, and the target is here and here. So I see that the first one supposed to be left unchanged, so 0, 0, 0 state, and the second one, we've got control 1, so we flip the target, so it's state 0, 1, 1 now. Okay. So what happens in the first layer? So the first layer is the application of the CX gate to the second and the third qubits in the circuit. So CX 1 over square root of 2, 0, 0, 0 plus state 0, 1, 1. Okay, so where is my control and where is my target? So control here, target here and here. So the first one, we leave it unchanged. The second one, I change the target, flip the target. Okay, so this is exactly the the GHZ free state. Okay, so generalization of the Bell state. So it's a perfectly entangled state of free qubits. And taking more qubits and applying more C0 gates, we can entangle more qubits in the circuit. All right. Yeah, so we discussed these things. Oh, by the way, let us go maybe to the IBM Quantum. right? And and check that our calculation is our calculation is right. So yesterday we discussed that applying the Hadamard and the CX gate creates the superposition of 0, 0 and 1, 1, which is the Bell state, right? So today we discuss this GHZ state, and it requires adding another qubit to the system and another CX gate, right? So the result is exactly what we expect to get, the superposition of state 000 and 111. Okay. All right. So now I suggest that we spend more time and to practice the the Qiskit. So IBM Quantum uses Qiskit. For those of you who are so you supposed to get your IBM ID, right? And using your IBM ID, you can log in to the system over here on the right. And as you get to as you get to this IBM Quantum platform, on the right upper side, you can find this IPI token. So basically, this is a very long number that you gonna use to send the or execute the programs, the algorithms on the remote quantum machines, quantum computers. Okay, so I copy this API token and go to IBM Quantum Lab. Okay. So here in this IBM Quantum Lab, I choose this Python free. Right, so IBM Quantum uses Qiskit, which is written in Python. Yeah, and so by default, this this first cell it gets this most important libraries to be imported, right? So I import them. Okay, and so all the work here. Let me actually import from Qiskit everything from Qiskit import all. Okay, so I have all the all the library imported, and in particular I can also import the from diskets import IBM Q function. Okay. Why? Because now I want to. So I plan to submit this project to the quantum computer, and I plan to use my token. So I need to. So I need to write this line IBM Q, then save the project to my account. So save account, and then in parentheses, I use this token. In your case, it's gonna be another string. And I also add this command overwrite true. So it's gonna be replaced if needed. Okay. So now I said that the program that I'm gonna use this token. And now I need to load the account IBMQ load account. And in a few seconds, yeah, I am in my external IBM account. So any user who register in the system and gets this token gets the remote account to, I mean, in the IBM Q system, and so using this line, I get connected to my IBM Q account. Okay, so how we draw the quantum circuit? Okay, so first of all, we need to initiate the quantum register and give it some name. For example, Q register, and we create the quantum register by writing quantum register and give it a name, give it the size of the register. Let's make it 2. Okay, so it's gonna be the 2-qubit circuit. And also for the circuit, we need the classical register. So I write C register, and it's also created by similar line, similar command, classical register. And let's make it also the size of 2. And the last line that creates the circuit is we give it the name. Just traditionally it's just circuit, and the command is quantum circuit. And in this quantum circuit, we put these names of quantum register and the classical register. Okay. Quantum quantum register. C. Oh. register. Okay. Okay. So these three commands create the quantum circuit, which is now empty. So in order to store the the circuit, so first of all we need to import this line to I mean, in the Jupyter, it's supposed to be working without this line, but in general, we need to write this line matplotlib inline to be able to see the graphical elements in the in the cells. Matplotlib inline. Matplotlib inline. Again, no need to write this one in Jupyter, but in other programs, it's needed. So I can show up my circuit. Circuit by this common circuit draw. Okay, so it shows me the circuit with two quantum qubits, 0 and 1, and the classical register C over here. Okay, so now this circuit is this quantum circuit is empty, and I need to add some gates to it, right? So I add gates to this circuit by command by the name of the circuit, and then that. So as an example, let's consider this golden 2-qubit circuit, right? So the first gate is Hadamard gate H, and I need to specify the the qubit that it acts on. So we act on the qubit 0. So I first get the name of the quantum register. Okay, so I put quantum register and specify the number of the qubit. So it's going to be the 0 qubit. And also write circuit draw to show the result. Okay, so we just added this Hadamard gate to the circuit. Okay, so what's next? We also need to add the 2-qubit gate, which is CX gate, and CX gate gets 2 qubits, the target and the control. So the first one is control, it's supposed to be 0, and the second one is target, it's supposed to be 1. Okay, so it's first 0 qubit and qubit 1. Apply and see. Yeah, so this is the circuit that I get. For the computations, we can't leave the circuit like this. We always need to put the measuring gates to the end of this circuit. So the measurement gates are added by the common circuit, the name of the circuit, then that and measure. And it also gets 2 parameters. First is the name of the quantum register, QREG. And the second is the name of the classical register, C rec. Okay, and this line again shows the result. Okay, yeah. So this is the 2-qubit golden circuit that creates the Bell state, right? And these two measure gates, they do the measurement and return the result of the measurement to the classical register. So the classical register is shown by this double line, okay, and yeah, and of course the quantum bit or qubit is shown up by this bold black single line. Do you have any questions so far? If not, then we can proceed with the simulations of this circuit. So in IBM Quantum, we can do either classical simulation or quantum simulation. So the classical simulation, it mimics the operation of a quantum computer. Okay, so it is the use of classical computers, but using some models for the statistics, right? So for the statistical properties of the results. All right, so let us start with the classical simulation, and then we will also consider the quantum simulation. So in order to use the classical simulation, by the way, classical simulation does yeah, it also requires this token. Okay, so any type of simulation that you send to the IBM machine, either classical or quantum, you need to use this token. So classical simulation. So in order to use the classical simulations, first we announce it and give it a name. Simulator. Let's give it a name. Oh, cool. Classical. Classical. Okay, we're gonna use this custom simulator. So the IBM provides several types of different simulators. We're gonna use this custom simulator, and I announce this in this way: ir.get backend, and the backend, I give a name of the simulator. So as I said, we're gonna use this custom simulator. Okay. Sometimes this line doesn't work because you probably need to import this operation IR from Qiskit. So if at this step it doesn't work for you, you can write something like from Qiskit import IR. Okay, and then execute this line once again, and it's gonna be working. Since I use this from Qiskit import everything here, it works well for me. All right, so now I can execute this circuit. okay, and represent the results of this execution. So let me assign, let me give a name of the result to the result. So result C, classic, result of classical simulator. Okay, and the command of execution is execute, and then in parentheses the name of the circuit. The name of the circuit is just circuit. Okay, and then comma and specify the backend. The backend in our case is this simulator simulator C we introduced here. Okay, and I need to convert this result to okay, and I need to convert this result into the actual result. Okay. Okay, so the circuit has been executed. Now I import from qiskit.tools.visualization. I import the histogram, the plot histograms, histograms. Histogram to be able to present the results of this simulation in form of the in form of the histogram. Yes, and using this command plot histogram result C of classical simulator. See, then I get the counts. Okay, counts and the name of the circuit, which is just circuit. Okay, so this is the result of this simulation of quantum circuit using the classical machine. Since this circuit is simple, just 2-qubit circuit, it can be easily simulated by classical machine. But this process of measurement is so this this simulator, custom simulator, we can actually, so for any information, of course, you can click help or go in Google for the information about the simulator. So for example, this custom simulator, basically all the specifications are here. So one can read and see how exactly this simulator implemented. So the idea is that the result of this classical simulation is very close to the result of the operation of quantum computer in terms of the measurement. So for example, this result, you see that 517 times the result was the state 0,0, and 507 times the result was 1,1, but nothing in between, because these states are entangled. Okay, you measure the one of the qubits and it automatically collapses to one of the states from the superposition. Okay, either 0, 0 or 1, 1, but nothing in between. You will see that after the quantum simulation using quantum machine, we will get the other states, state 0, 1 and 1, 0, because the real quantum computer is not perfect system, not perfect machine, and the entanglement, of course, not perfect there. So you always get this extra states. But classical simulations give us the only 0, 0 and 1, 1 because we prepare the perfect Bell state using this golden 2-qubit circuit. Okay, but the fact that we didn't get the perfect 50 50, like 50% 0, 0, 50% 1, 1, is the manifestation of the approaches that this simulator uses. So this custom simulator introduces some amount of randomness to the circuit. So we've got not the perfect result. Okay. Another point here is that this works pretty good for 2-qubit circuit, 3, 4, 8-qubit circuit, but the circuits of higher dimensions, of higher number of qubits, cannot be simulated using these classical circuits because they still classic, they just mimic quantum, and the problem becomes, the complexity of the problem scales as a exponential function. Okay, so the 8 gates is 8 qubits is already a tough problem, and if you increase the number, you cannot basically simulate, you cannot use this type of solvers. And for example, circuit of 50 qubits is already unsolvable by classical means, by classical computers. Okay, but IBM gets computers with much more qubits and much more gates than can be handled by classical computers. So these quantum computers already simulate things that are not takeable or not solvable by classical computers. Okay, so by default, this, so what these counts mean? Okay, so by default we get the number, how many, 1024 counts, and each count is the result of one single measurement, one single run of the circuit, and the program runs the simulation 1024 times, okay, to build the statistics, and of course we can change this amount of shots, of runs. And to do so, I just specify these results here. Just after this backend, name of the backend, I add the number of shots. For example, it was 1000, so let's increase it to 2048. 48 by twice, right? So I run the simulation, and I can now represent the result. So now you see that 1,000 times roughly the result was 0, 0, and 1046 times it's state 1, 1. Of course, if I run this simulation again, I will get different another numbers. Okay, if I run it again I get the different numbers, another numbers. But what roughly stays the same is the dispersion, like how much, what's the difference between the two, because this number is very, very large now. I can increase this to 5,000 and get even smaller, smaller dispersion. So now they are like completely the same. The percentage of the difference is very small. But of course, if I make this number smaller, I can see that the dispersion gets increased, right? So now the dispersion is in percentages, it's like 10%. And if I take it, make it even smaller, the result can be very, so now the dispersion is maybe, yeah, more than 50%. So we came to an important conclusion that in order to get rid of the statistics, like this randomness in the result, we need to do as many runs as possible, right? And only in this case we get the result that is theoretically predicted. So for the theoretically predicted result for the golden 2-qubit circuit, in our case, is 50% 0, 0, 50% 1, 1, and nothing in between, nothing, no contribution from state 0, 1, no contribution from state 1, 0, etc. All right, so now we can, so this was the classical classical simulation. Now we can run the real quantum simulation, real quantum simulation. Let me turn this one to text. Yeah, real quantum simulation. So in order to run the real quantum simulation, we need to specify the provider first. And in our case, provider is IBM Quantum. Provider. And in our case, it is IBMQ. And we get the provider with the name IBMQ. So now in our case, this line is always like this. Provider, the name of provider. And then we need to specify the particular computer. Okay. So in order to select the quantum machine, quantum computer, we go to the platform and here, these simulators. Okay, simulators and all systems. Navigate to all systems. So all system contains all the quantum computers that actively I mean, available, but not of them available for the education purpose. Okay, for example, I can arrange these quantum computers by the number of qubits, and they, I mean, of course, the computers with the largest number of qubits that are available for the simulations, So today it is 127 qubits. This is not the largest quantum computers available today. The largest one contains around 400 qubits. Okay, but for computers that are available remotely start from 127, and the smallest number is 7. Okay, 7 qubits. So this list changes quite periodically. I recall the time when this list contained the number of maybe 4 qubits. So now, yeah, so now it's much more, but unfortunately, not of them are available for our education purpose. For example, this one, the largest one, provides access only through this premium plan. So you pay, you use. Okay, for some, for example, research, we can pay for this system and use this for quantum simulations, but not for not for the education purpose. For education purpose, we have this one available, IBM Brisbane, but this machine is pretty busy. So today, right now, there is a 147 jobs in the line. So we probably search for another machine. But we can also look at the other specifications here. This median times T1 and T2 we discussed last time, right? So T1 is the decay time. So basically how fast the energy of the state decays by a factor of E. The median T2 time is the average decoherence time, and this T2 time is the most important parameter of any qubit, because it basically tells us the time the qubit can keep the quantum information, quantum coherence. Okay, so this is the topology of this particular quantum computer. Some of the so the qubits differ in color for the purpose of of different error, because of course these qubits they differ because of the fabrication and edging, right? Edging the system after time being used, system of course degrade, and different qubits degrade with different rate. So yeah, and this system, there is a feedback system that controls the parameters of each qubit in the system, and you can use it, and you can see it here. So this machine is good, but it's too power for our purpose, and it's too busy for now. So let us maybe look at the smallest online reserved, this one online, and looks like available for simulation. So I suggest that we use this one. It gets 34 jobs. This one gets 1,882 jobs. So this one is very busy. This one is 8, but again, only premium plan. This one not public, currently not publicly accessible. Okay, so let us use this one then. IBM Lagos. So I go back to this IBM Quantum Lab, and I choose the quantum computer. So I already requested my account in IBM Q by these two lines, right? So I already have account there, and I specify the particular computer, quantum computer, name of of this provider, and then I write get backend, and the name of the backend. In our case, this backend is the IBM Lagos. Okay, let's hope it will connect to the computer. Okay, yeah. And now I create a job to put in line for this particular quantum computer. Okay, so I named this job like job, and I write execute. Execute what? The circuit, and our circuit gets the name circuit. And I specify the backend. And backend is this one, quantum computer. Okay. Good. So I just sent this this problem to the quantum computer, and as far as I see, this job is already executed. Looks pretty fast. But I still want to download this import this job monitor, so I can see in online in real life the status of my project. So from Qiskit tools monitor, I import job monitor. And I initiate the job monitor for my for my project. Job monitor. Okay, so my job is in line, but it says none. Interesting. Alternative form of no. So it says none. It doesn't say how many machines in the line. Interesting. Okay, let's wait a couple of minutes then. So usually when it says the job status, it shows the number of machines or number of jobs to be executed before the system gets to your project. Okay, so while it's running, in the line, you can see the job status also here of all of your projects. So I see that this one is pending and in the line. Yeah, so problem with this one is that I don't see how, I mean, I don't see the progress. And I'm not sure how long we supposed to wait until we get the result. But while still running, let us maybe go to to these quantum computers, to this list, okay, and see what else we have. Like, so I also can arrange these quantum computers by this quantum volume, and this is another QV, quantum volume. This is another important parameter of quantum computers. Okay, so the quantum volume is a metric that is used to quantify the power of a quantum computer. Okay, so the number of qubits is a important parameter, but it's meaningful in terms of the computation powerfulness. Okay, so the it depends on the topology of the quantum computer. The qubits, so it's not a problem to create a system with 1,000 qubits, for example, but and some of the currently existing systems contain thousands of qubits. But the problem is that they are not entirely entangled. Okay, so these systems with less number of qubits, like 20, 100, these systems have qubits that are fully or partially entangled, mutually entangled. And the computer can change or vary these the strengths of the entanglement between the qubits. Okay, so the number of qubits is not the crucial parameter. What is more important is quantum volume. So basically, quantum volume quantifies the largest random circuit of equal width and depth that the computer can successfully execute. Okay, so this quantum volume describes the size of the quantum circuit that it can execute. The larger this number, the better. So what is the product? Still online. Interesting. So this is how we prepare the circuit for simulation. And of course, there is another way. Okay, so we are 24th. Let's see if this number changes. Okay, so still 24th. So this is how we prepare this quantum circuit in quantum lab. But of course, there is another option here to use this quantum composer. Okay, and using quantum composer, it's much easier to do the job. For example, the same circuit can be easily created by tagging this Hadamard gate and this C NOT gate here, and adding the measurement gates here and here. Okay, and as I change the circuit, you see this Qiskit code on the right. It also changes accordingly. Yeah, so it's much easier to to prepare a circuit in the composer, and then you can open the circuits in the quantum lab by clicking this button here. So what it prepares the basically all the lines that you need to run the execute this circuit. From the Qiskit, it imports the quantum registers, classical registers, and quantum circuits, and some mathematical required mathematical operations from NumPy, like constants, right? And then again, it creates the quantum register of size 2. If I add another qubit, third qubit, it will automatically it will automatically change this line here. Okay, so I add the third qubit in this circuit, and it changed this number here. So let us remove this one. Still 24th. Interesting. All right. Okay, so and this way, of course, you can create the circuit of like much more complex circuit. For example, the GHZ state of 4 completely entangled qubits. You see this perfect superposition of 4 0 for 1 states. Okay. And then what you do, you must add the measurement qubits or measurement gates, sorry. Okay, and then you just click open in quantum lab, and it creates the quantum lab code that you can run. So by default, it's just copy this code here. I can execute this code, and it shows me the composer background, right? And I can also enable this one, so my code can be adjusted right here, and it will be rewritten accordingly. Okay, so it's very useful. And then again, if I want to run this one, how many jobs? Still 24. Maybe that was not a good computer. It's still running. It looks like it is inactive. So let me try to find another one. So this one was IBM Lagos. IBM Lagos. Let me try maybe maybe this. Oh, this one not. Hmm. Okay, let's try this one then. IBM Brisbane. So what I do, I can send the same job, but to another computer. Let's give it another name. Please. Uh, provider is the same, but another computer. Okay. And I send another. Yeah, this line can be executed while this job is pending. So okay, let me let me cancel this one. And remove this one. And this line. Not a good day for quantum simulations. Okay, I remove this one. Bring it here. Access the provider. Oh. Okay, I can restart the kernel and execute the lines again. Shut down the kernel, restart the kernel. Hmm. Yeah, apparently, oh, okay. Apparently some issues with the server or something. Anyways, so can I use the same? Okay, my account. Okay, the circuit. Yeah, should I create a new one? Okay. Then I skip this classical part, connect to the IBM Quantum. New machine, Brisbane, job, new computer, circuit, monitor, job, oops, job monitor. Okay. One more try. So now it's again says none. And I wonder why. Okay, so we asked position number 6. Oh, estimation wait 3 hours. Estimation wait 3 hours. Oh, wow. Yeah, estimation wait 3 hours because the system is apparently very busy now. A lot of people today use these quantum machines for simulations and for education. Of course, not only our group interested in simulating the things. So I suggest that we look at the result of the quantum simulation. This particular one next time we meet. And let me maybe just summarize the things by stating that we can we can create, for example, using Composer, we can create a much more complex circuit, for example, like this one, right? And then opening this one in Quantum Lab, we can run the classical simulations that mimic the quantum computation or run the actual quantum computer. So let me summarize the first one, the classical simulation. Setup. Right, in order to set up the classical simulations, I first import everything from the Qiskit. From Qiskit, import all. Right, then I announce the simulator. Simulator. And choose the particular simulator, IR. Get backend. And as a backend, we use the name of the simulator. So usually we use this custom simulator. It can be, by the way, found in the simulators. So here we have all the available simulators. Our custom simulators are over here. The names of the gates we can run using these simulators. The maximum number of shots, 20,000. And of course, you can read more about this one. Yeah, you see a general proper simulator for simulating quantum circuits, both ideally and subject to noise modeling. The simulation method is automatically selected based on the input circuit and parameters, which is nice. Okay, so the custom simulator This is the simulator. We announce the simulator. Then we need to get the results from the simulator. By executing this circuit. In this case, the name of the circuit again is circuit. Okay. Backend is our name of the simulator. Simulator C. And then we get the results. Okay, this is the third line. And finally, yeah, we can execute this one. And finally, from Qiskit tools, Qiskit tools visualization. Import plot histograms. Histogram. Import Qiskit.tools visualization. Import plot histogram. Okay. And finally, we show up the plot histogram. From the results, name of these results. And we get the counts of the for the circuit, for our circuit. Okay. So this is the setup of the classical simulation using the IBM quantum simulators. I mean, of course, one can use different types of simulators from the list. Depending on the purpose, one can choose between among them. For example, this one, simulator MPS, specifically for the tensor network simulator that uses a matrix product state representation for the state. So the simulators they differ in terms of their purpose. This one, for example, for the Clifford simulations. Yeah, so one can use the one that works specifically for their purpose. One can also specify the parameters of the simulations and other things. So all this information can be found on the Qiskit website in documentation, tutorials, or the documentation. And this is the setup of the classical. And let me also write down the setup for the quantum, because in your homework you supposed to run the both classical and quantum, get the results, and write the basically comparison of the two. This is the this will be the lab work one, the first lab work assignment. So the quantum setup. It's 2 hours. It says 2 hours. So it definitely less than 3 hours is not going to be 2 hours. It's going to be less than 1 hour, maybe half of the hour. But you see, we need to wait some time. Yeah, quantum setup. In order to run the quantum setup, we first of all we need to, if we start from this point, from the quantum composer, and then transfer the code to the quantum lab, then we need to connect to our provider, right? So we have to write from Qiskit, we import IBMQ from Qiskit, import IBMQ. Then from the IBM, I connect to the account, right? IBMQ save accounts, and then I use my token from the first page, right? Copy, copy and paste in the quotes, between the quotes. And then I specify our write true, write true, over write true. Okay, and finally I load my account, IBMQ load account. Okay. So it says it's gonna be changed somehow, but for now it works well. And this line basically indicates that I am connected to my account. All right. So then I choose the provider. In our case, this is IBM. Provider IBMQ. Let's get, and the name of it, IBMQ. IBMQ. Then I specify the quantum computer. Quantum computer. Provider. Get backend. Backend and the name of the backend, name of the computer. So again, we go to the list of the available computers. And let us select another one, maybe. Yeah, so they restricted the access to their computers. That's pity. That's pity. All right, IBM Perth. Let's go this one. Let's use this one. So IBM Quantum. Then I initiate the job, giving it name, execute circuit. Again, this circuit is the name of the circuit that you imported from the composer. Circuit backend. Back. and the backend name is our computer here. Okay, from Qiskit, I import the monitors. Qiskit tools import job monitor. And and initiate the job, launch the job monitor for this job here. All right, this is another project we just started. Let us see how long it's gonna take. This one's still 2 hours. This one, not sure. Okay. All right, so anyway, today we explored this IBM quantum platform and how we can prepare, how we can draw the circuits, build the circuits, and simulate them using the classical simulators that mimics quantum, and how to send the job to the real quantum machine. So we will discuss the results of these simulations next time we meet. And I will make the assignment for the first lab work that will be close to what we have done today in class. Okay, so let me stop the share and stop the recording. Thank you.